Other questions? Okay, so if not, let me begin. So last time I mentioned that there is a close connection between the Riemann tensor and parallel transport around the loop. Okay, so today we'll try to make this more specific. Okay, what exactly the connection is. Okay. So what we'll start with is a small loop. Okay, so let's suppose that we have some point x naught, and you take a small loop of length of order epsilon. And since the metric is finite, okay, if the loop has length of order epsilon, that means the coordinates change by order epsilon as you go around the loop. Right? The coordinates move away from the origin by order epsilon. So we want to parameterize this curve first. And we parameterize it by this variable u. Now normally we had said that we'll choose u so that the beginning of the curve is at u equal to 0, the end is at u equal to 1. If we choose it this way, we can, there is nothing which prevents us from choosing it this way. If we choose it this way, then dx du along the curve will be of order epsilon, right? Because as u changes by order 1, right, x changes only by order epsilon. Okay. So we'll try to avoid it by saying that u runs not from 0 to 1, but u runs from 0 to epsilon. So we just scale u so that you basically multiply u by epsilon. Okay, call this your new u, so that u runs from 0 to epsilon. Okay. So we denote by xi of u is the curve with 0 less than equal to u less than or equal to epsilon, okay, and xi at u equal to 0 is xi naught, and xi at u equal to epsilon is also xi naught. And with this normalization for u, dxi du is of order 1. Okay, because when u changes by order epsilon, xi moves around by order epsilon. Okay, at the end, of course, it comes back to the original point, but dxi du is of order 1 along the curve. So this will be useful because we will try to estimate, we will try to calculate the change, okay, the parallel transport. Okay, our goal is to understand parallel transport along this curve. Okay, so we'll calculate the change in the vector as a power series in epsilon. Is this clear? So we have, so ni of u is some vector satisfying dni du and let's say ni at u equal to 0 is some ni naught. Okay. And the question is, what is ni at u equal to epsilon? Okay, this is what we want to calculate. Okay, and we will calculate it for small epsilon, okay, in a power series, and we will see that we will keep up to certain number of terms, okay, so certain parts of epsilon, and then not worry about the higher parts, okay, for reasons that will become clear later. Along this curve, right? Initial vector is some ni naught, some arbitrary vector, right? We are parallel transporting it along this curve, and you want to know what happens to it as you come back to the original point. Yeah, it's just order epsilon, right? Because metric is a finite number. Gij right, is some finite number. So if the total length is of order epsilon, right, then the coordinates also change by order epsilon, because the ds square is gij of x dxi dxt, right? This is epsilon square, right? So the change in x should be of order epsilon, because this is finite as epsilon goes to 0. Yeah, that's why we will not, because we are just counting parts of epsilon, we will not worry about whether the distance is real physical distance or whether it is just a change of coordinates, right? How much the coordinate changes, because both are of the same order. Okay, gij is just some extra factor that multiplies it. Okay. So the idea is that we will try to solve this equation. Okay. But because we are interested only in small changes, okay, we will try to solve it iteratively in powers of u. Okay, so first let's try to calculate the order u term, okay, in the solution, right? So ni of u will be, to begin with, it will be ni0 plus something of order u, right? And then something of order u square and so on. Okay. And since u is of order epsilon, right, that expansion can be converted to powers of epsilon. So iterative solution, we solve it iteratively. So the first iteration, so what we are going to do is that we will write this equation on the right hand side. We will only keep terms of order u to the 0. Okay, only u independent terms, because then when you integrate it, right, you get terms linearly do. Right? Then you are going to substitute it back again on the right hand side and solve it again to get terms of order u square. Is that procedure clear? Right, because we are trying to integrate this, right, from u equal to 0 to some small number, right, say u, right, which is of order epsilon. To do the integration, right, if the right hand side already contains a term of order u, right, then the integral will give you u square, right? That becomes a higher order, right? So first let's try to determine the order u contribution to ni of u. Okay, then we will worry about the order u square. So for this, on the right hand side, we can just set u equal to 0. So this is given by minus gamma ijk x naught nj naught, because at u equal to 0, this is nj, and dx du will keep as it is. Which one? Dx du is of order 1. Oh, right, because that's how we have chosen u. Okay, so let's just keep dx du. So we integrate this. This is easy to integrate. So ni of u will become ni 0. This is the initial condition at u equal to 0, right? And then you have to integrate this from 0 to u, right? I call this u prime. So that gives you times minus gamma ijk x naught. Sorry, I forgot the bracket here. So ni naught minus, and this when you integrate from u equal to 0 to u, okay, it's basically xk of u minus xk naught. The change in xk as u goes from 0 to some arbitrary value. Is this clear? Right. The right hand side is of order u because this is of order u. dxk du is finite, right? So xk of u minus xk naught of u, xk naught will be of order u. Right? That's what you want to get. You want to get the order u contribution to the right hand side. nj0, yes. Oh, yes. Thank you. Okay. Now we have to solve it again. So second iteration. So there is an order U square correction, which you haven't calculated. In the second iteration, okay, let's write the equation again. dni du minus. Now on the right hand side, go back to this equation. Okay. On the right hand side, we have to keep terms of order U up to order U. Right? So gamma ij k x of U have to expand in powers of U. Okay. Similarly, these have to expand in powers of U. Okay. These I'll keep as it is, dx k du. Okay. So there is no expansion that we will do for this term. So this can be written as minus gamma ijk x naught plus it's enough to keep up to this term. Okay, next term will be order U square, right? So which will contribute here. After you integrate, it will give order U cube contribution, right? Which is not what we are looking for. So this we expanded like this. So Nj, okay, we have to expand to order U, right? But we have already found Nj to order U, right? So these are, we are going to substitute this. So times, okay, except that I have to be careful about the indices. So this Nj is what we're looking for, right? N0j minus gamma j. Okay, let me change all the indices. This is so mn x naught n naught m xn v minus xn naught. Okay, and finally dx k du I'm going to keep as it is. Plus order U square. Okay, so if we integrate this, we will get order U cube error. Okay, because order U square term we don't know what it is.
First part of the Excel should be Excel of U, right?
Yes, yes, indeed. Excel of U. Thank you. Excel of U. Everything. Is clear? So you are now going to expand it out because you see this is already of order U, right? So to take the product of this and this, it becomes order U square. That term you can throw away, right? So you only have to keep the cross terms. So first these terms, this of course you have to keep. Right? That's a leading term anyway. And then these times this have to keep, and these times this have to keep. Okay, so let's try to do that. So we get dni du. First, let me keep the leading term minus minus Yes. Which is okay, doesn't matter. If we keep higher orders, right, we are not changing the order u square result. We want to make sure that order up to order u square the result is correct. Right? If there is some additional order u cube term, we don't care, right? We fix it in the next order. But we don't want to, we are not expanding dx du at all. We are writing dx du as a function of u. That is the exact result, right?
Okay, you're always using the exact.
Exactly. But dx du, you are not expanding. I mean, it's my choice, right? If I want to expand or not. I mean, if I can solve it by using the without expanding, it's fine. May not be a constant. You see, here we had, as didn't assume that it's a constant, right? That's why you got this term. Yeah, dx du is of order 1, right? But the derivative with respect to u may be order epsilon, right? We don't know. Okay, but we just don't want to expand this, right? Because dx du we just keep as dx du, right? See, as long as I'm not expanding, as long as I'm keeping the exact result, right? There's no confusion. I mean, I'm not making any error. I mean, I want to expand because things simplify, right? But for dx du, I don't want to simplify things, right? It will be simple as it stands. Is this point clear? So this is one term. Then I get this cross term, right? This one. So that gives you plus gamma I jk x naught is clear. I picked this term, that is the first term, right? Then I picked this cross term. Sorry, that's the next one. The second, then I picked this cross term, right? That's the second line. Okay. Then I picked this cross term, that's the third line. Okay. And this times this I can ignore because this is of order u square already. Okay, order u square term I'm not keeping on the right hand side. So now I can integrate this, okay, and get ni of u with an error of order u cube. Right? Because order u square, when you integrate from 0 to u, right, you get order u cube error. Okay, but we are, let's say that we are, for some reason, right, which we'll make clear later, that we are allowed to make order u cube error. Okay, we only want the result to order u square accuracy. So if we accept that for now, right, why, as I said, I'll explain later. Then we can directly go to our final goal, right? Because you want to calculate ni of u at u equal to epsilon. So let's just integrate this all the way from u equal to 0 to u equal to epsilon. Okay. So this tells us that ni at u equal to epsilon will be given by ni naught, that's the first term, then minus gamma I jk x naught okay. If I had wanted as a function of u, I would have written xk of u minus xk naught, right, as we had done here. Okay, but now I'm writing it directly for x u equal to epsilon. So that's that term. Then I have minus. So here I want to change things a little bit. Okay, let me do this anyway. Gamma I j k x naught xl of u sorry, I cannot do this. Let me I'm writing this one, right? These are u independent. So these I take out and then I write integral 0 to epsilon du right? That's the second term. But I'll do something slightly different. I'll write this as x k of u minus x k naught. Because this is u independent anyway. This is just a constant initial position. Right? So ddu on x doesn't gives you just 0. Okay, so instead of writing ddu of xk, I'm just writing ddu of xk of u minus x naught k. Is clear? Now the third line, okay, so we are going to do the same thing on the third line. Third line, I'm going to change things a little bit because so that the indices match. Okay? So m I'm going to change to j. Okay. Yeah. So j and m I'm going to exchange. Okay. I'll change m to j and j to m. Okay. So let's do that right here. I'll call this as summed over index anyway. So this I'm going to change to j, and this j I'm changing to m. Okay, just to make sure, I mean, bring it into this form, right? N0j. Similarly, this here you have xn, the dxk du is common, right? This I can write as ddu of xk as before. Here you have xn of u minus x naught n, right? In this line I have xl of u minus x naught l. So I'm going to change n to l. N to l is allowed? Yes, because l is not there anywhere, right? So I can change n to l. Let me use a different chalk. So I'll change this to L and this to L. Okay, just repeat it summed over index, I can rename. So with this, and then the order E plus order E plus order U cube, epsilon cube, right? Because U is epsilon. So order epsilon cube terms we have not calculated, let's leave them aside. Okay. So this I can write as N0I. Pardon? Oh, I didn't write. Sorry. Yeah, I have to write. Thank you. Plus, yeah, I'm going to put a bracket, except that in this line, probably putting a bracket is not a good idea. Let me write this out. Pardon? Exactly. So two integrals look the same, right? Two integrals look the same. Also, n0 carries the same index. So n0j, and then I have the same integral 0 to epsilon du plus order u cube, order epsilon cube. Is this clear? So these two terms I can now combine. Okay, so let's leave the coefficient of this aside. So this part is common. The common part, let me identify. So this part, these parts are common, right? Sorry, even this. So they are the same factors in both. Okay, let me draw a line here so that it's clear that these are two part of two different things. Okay, so this was a factor that appeared in the this line, second line, and this is the factor that appeared in the third line. They are the same factors. So you keep them outside, and then I'm going to combine these two. So when you combine these two, you get minus okay, just sum of this and this. Yes, yes, thank you. JL. Now, if you remember the expression for the Riemann tensor, right, you recognize that this is half of the Riemann tensor, right? Riemann tensor had two terms like this and two terms like this, right? If you compare, you will find that this is half of the Riemann tensor, right? So you have not, our goal was to write in terms of the Riemann tensor. Okay, so you are not there yet. Is this clear? Okay, the Riemann tensor has a derivative of gamma and then a gamma gamma term, right? But two of those, right? Two of these terms like this and two of terms like this. But now I'm going to make another observation which will be useful, okay? And that is that this combination is antisymmetric under LK exchange. Is it clear why? Suppose you change this into K and this into L. Yeah, so you have to integrate by parts, right? So if you integrate by parts, right, ddu acts on this. Okay, so it gives you the minus of the same thing with LK exchange. Okay? But what about the boundary terms? Right? The boundary terms vanish because this vanishes at the boundary. Right? At u equal to 0, of course, is vanished, right? Because it's x naught minus x naught. But at u equal to epsilon also, this is 0. Right? Because at u equal to epsilon, you are back to the original point. Right? So x of epsilon, xl of epsilon minus xl0 is 0. So let me write this. So integral 0 to epsilon which I can write as minus integral plus the whole thing, sum of this evaluated at u equal to epsilon and at u equal to 0. So xl of epsilon minus xl0 times xk of epsilon minus xk0 minus this is the result of integration by parts. Okay, we transfer the derivative to the other side and then we take the difference between the integrand at the top and the bottom limits, right? Epsilon and 0. But xl0 is x naught L by definition. At u equal to 0, that's where you start. What is more important is that xl at epsilon is also x naught L, but it's a closed curve. We start with x naught, and by the time you reaches epsilon, we have come back to the original point, right? Remember this curve. Right? These are our x naught. Okay, so this is also 0. So both limits vanish, right? You integrate by parts, and the result is that you have essentially exchange L and K with a minus sign. Okay. So this shows that this quantity is antisymmetric under the exchange of L and K, which means that whatever multiplies it, which is here, only the antisymmetric part of this will contribute, right? So I can write half of this minus the same thing with L and K exchange. Yeah. So here, let's call this in this tensor, whatever appears here, okay, as some ALK, okay, or AILK, right? There's an I free index, AILK. AILK multiplies this, okay, L and K are summed over. Okay. This, whatever it multiplies, is antisymmetric under L and K exchange, right? So which means that the only combination that contributes, suppose you write AILK, let me this one. Let's call this expression that we have gotten here. Oh, by the I should just say that by that argument, the first term is 0, because xk of epsilon minus x naught k is 0, right? So no order epsilon term in this, only order epsilon square is a leading term, right? Which is what we are trying to calculate. So what I was trying to say is that let's call whatever appears this combination, right? Let's call this A I L K. Okay. J should also be there. Okay. A I J L K. Now the expression that we have is A I J L K N naught J, and then integral 0 to epsilon du xl of u minus xl naught du of xk of u minus xk naught. Now this one I can always write as half of AI JLK plus AI JKL plus half of AI JLK minus AI JKL. So the second terms is cancelled anyway. Okay. This is symmetrized, this is symmetric form, this is antisymmetric form under JL exchange, sorry, under KL exchange. Now when this multiplies this, the result will vanish, because I can change the sign of this by exchanging L and K, right? This one doesn't change under change of L and K. So this one multiplying this antisymmetric term will just give you 0. Only this one will contribute, which basically means that in this expression that I have gotten, I can antisymmetrize in L and K. Right? Instead of writing this, I can write this as half of this minus the same thing with KLN exchange. Is this clear? So let me write the expression for Ni and then it will become maybe clear. So this expression that I have got, I'll write as Ni at U equal to epsilon is equal to N naught I. Okay, this term goes away, this is 0. And then plus half of these two terms minus plus last to the JK. Yeah, okay, thank you. Yeah, K and L are exchanged. N naught J, thank you. Yeah, this whole thing. Is this clear? Right, I have just antisymmetrized this combination, right? That's the only thing I have done. And the argument is that this, whatever multiplies this, that is antisymmetric under LK exchange. So this one, okay, if you look at your notes, I think this is R I J K L. Okay, if I remember the sign that I defined, right, this is R I J K L. Is this clear? So what this is saying is that if the Riemann tensor at x naught vanishes, then this parallel transport along a closed curve gives you term of order epsilon cube. We don't know if this term is 0 or not, but at least up to order epsilon square, there is no term. Is this clear? Right. So vanishing of a Riemann tensor at point x naught shows that parallel transport along a closed small loop around that x naught is of order epsilon cube, produces something of order epsilon cube. This I can write now in terms of the matrices that he introduced. So remember this definition, the x naught. If we call this curve C, then the matrix M starts at x naught, ends at x naught along the curve C, is identity matrix plus order epsilon cube. Because these are matrix that is supposed to multiply ni naught to generate the new vector. Right? And because this holds for arbitrary ni naught, right? We didn't say anything about what ni naught is. Right? That means the matrix itself, right, which multiplies ni naught to get ni at u equal to epsilon, okay, is identity plus order epsilon cube. Okay, so let me remind you how this matrix would have been defined. So ni of epsilon would have been m of x naught c times ni naught. Right? That was the definition of the matrix. Yeah, matrix indices will be there. Thank you. Yeah, Mij. Because it's acting on the vector space, right? That's the way you had introduced this matrix. And what we are saying is that because ni at epsilon is the same as ni naught, okay, as a vector, it doesn't change, right? Except by order epsilon cube terms. Okay, I mean, if you want to, I can write this way. Okay. But nevertheless, as a matrix, you just think of this as a row index and this as a column index. Sorry, yeah, this as a row index and this as a column index, right? That's the way you are supposed to multiply. Okay, similarly, I, okay, the ij element is delta ij, right? I is above, you write I above and j below. Is this clear? Okay. So let me say this again. So last time we had introduced the notion of this matrix, right? That along any closed path, not even closed path, along any path, okay, if you start with a vector and see what it happens after parallel transport, right? Because the equations are linear, we had argued that the final vector is some matrix M times the initial vector. That matrix depends on the initial and the final points as well as the curve that you follow. When you have a closed curve, then the final point and the initial points are the same. That's why you have the two arguments the same. But the result depends on the curve that you follow. And what we are saying is that as long as the curve is infinitesimal of order epsilon, this matrix is identity plus something order epsilon cube. Because of this fact that ni of epsilon is ni naught plus order epsilon cube. Should vanish at epsilon. No, because ni, this term is there, right? N0i. So identity matrix acting on N0 gives you N0. Right? So if you have identity matrix and acting on N0 will give you N0. Right? That's this term. That's this term. Right? And then order epsilon cube because there's nothing else at order epsilon square. Yes.
It should have been order epsilon square, right? That integral is supposed to be order epsilon square. Order epsilon is vanishing. Order epsilon square.
Yeah. If this is if maybe I didn't write this. Yeah, that if the Riemann tensor is 0, then this is true. Right? Otherwise, indeed, it's of order epsilon square. That depends on a particular space, right? You have to calculate Rij given a metric and see if it's 0 or not. Right? That depends on a metric. On the sphere, for example, you saw that the Riemann tensor is non-zero, right? Two-dimensional sphere. Flat space, it is 0. Okay. Yeah, the integral is something like an area, exactly. Area measured in coordinates, right? Not the area measured in the metric, right? Because this doesn't know anything about the metric. Right? So that is what is called the area element. Right? It will not be important for what we are going to discuss, but that integral is what is called area element. Right? In the if you take a parallelogram, right? take some parallelogram and evaluate that integral along the for this parallelogram, you will find that basically gives the area of the parallelogram, okay, in the coordinate space. Okay, it's also somewhat apparent from the fact that that integral is of order epsilon square, right? And the area is supposed to be order epsilon square. Okay, now as it stands, okay, this is of course a useful result, okay, but as it stands, it doesn't say anything about what happens in a big for a big loop. Right, our interest is in finding out M AAC. This is big, so obviously you cannot do an expansion like this. Right, epsilon is of order 1, right? So we don't know what order epsilon cube terms are. So a priori, this result by itself doesn't say anything about what happens in a big loop. But now we are going to prove the result that I mentioned last time. Okay, that what will prove, okay, using the infinitesimal result, small loops, we shall show that M A C is identity if we can find a surface S, a 2D subspace S, such that the boundary of S is C and R IJKL is 0 everywhere on S. 2D subspace that in 3 dimensions, for example, suppose this is a curve in 3 dimensions, right? There are many 2-dimensional subspaces that whose boundary is that curve, right? Imagine in 3 dimensions you have a curve, right? We can take a plane, right? If the curve is on a plane, but we can also have a basket length, right? So as long as you can find any surface of this kind on which the Riemann tensor is 0 everywhere, okay, then the parallel transport along the closed curve will give you identity. Right? That's the claim. Is this clear? Okay. So let me describe the general procedure that will follow to prove this. Okay. No, we don't have to. That's the point. We'll prove that this is identity, right, based on just the result we have found. Right? So that's the surprising thing, right? If we don't have to worry about the order epsilon terms, right? And we will see why. Exactly. Exactly. We'll see that it doesn't matter if you take them or not. Is this clear? Okay. So what is the strategy? The strategy will be the following, right? You take this curve C, okay, and imagine that there is some surface, right? I'm drawing it in a plane, but you don't have to imagine that it's not a plane. Right? It can be any surface, right, which binds this, and we just cover it with some fine nets. Shape doesn't matter, right? Anything that you draw is fine. So if there are, suppose there are n nets, if we have n segments, area segments, right? Let me call each of these area segments. These are the area segments, right? The total curve has finite length, right? Doesn't matter what the length is, that finite length, and this surface that covers the whose boundary is that curve, right, is also a finite area, right? The precise form doesn't matter how much that finite area is. Okay? It's a finite area. If we divide that into n segments, right, each segment will have area 1 over n. Total area was n, right? Sorry, total area was 1. Okay? Order 1. Okay? You divide it into n segments. So each segment will have area of order n, or 1 over n, right? Again, it doesn't matter if you are using the metric to calculate the area, right? Because order of magnitude doesn't change, right? Just you can think in just in terms of coordinates, right? In a given coordinate, what the area is, okay? Pretending that the metric is just flat, delta ig. So each segment, has area of order 1 over n. Area is also an invariant. Yeah, once you give the surface, it's invariant. I have not defined what area is, but indeed it is an invariant, right? But in this case, as I said, it doesn't matter, right? You don't have to use a metric to calculate the area. If you use a metric to calculate the area, then it's invariant under change of coordinates, right? But just think of calculating it, assuming that the metric is flat, delta ig. Okay? The result that you will get, right? Order of magnitude will be the same, right? Unless the metric is very big or very small, right? Order of magnitude is the same. That's what matters, because we are only interested in the n dependence, right? If you divide it into n segments, then each segment will have area 1 over n. So the length of each segment, or circumference length of each segment, which I'll call epsilon, is of order 1 over root n. Okay. So m for each segment will be identity plus order 1 over n to the 3/2. Right? This is order epsilon cube.
Everywhere inside R is 0.
Yes, indeed.
Starting with the
Yeah, exactly. This is the assumption, right? That on this surface, everywhere R is 0. Otherwise, there will be order epsilon square. Right? We are assuming that R is 0 everywhere on the surface. Okay, not everywhere in space, but just on that surface, everywhere it is 0. Is this clear? Okay. So what we are going to show, right, and it will take some effort to show this, is that m for the original quantity, right, AAC, this one, is roughly, okay, only roughly, okay, we'll make it more precise, okay, the product of m for each segment. Pictorially, it may feel appealing, right? That the inside lines are all cancelled out, right? When you take these products, right? So m is roughly the product of m for each segment. Okay? So then this is the product where I equal to 1 to n, okay, of matrices, okay? And each matrix will have the form I plus 1 over n to the 3/2 times some matrix bi, some matrix, but it's of order 1. Right? This result follows from this. because along each segment its identity plus order epsilon cube. Right? Order epsilon cube is 1 over epsilon n to the 3 half. Right? The epsilon is 1 over root n. Is this clear? So for large n, what does it become? It becomes identity, right? Because think of expanding this out, right? So the first term will be, of course, identity, right? Then you pick 1 over n to the 3 half from each, right? From one of them, identity from the rest, right? So you'll get 1 over n to the 3 half times sum y equal to 1 to n bi. And then you can expand it out. Oh, because epsilon is of order 1 over root n, right? And this argument shows that as long as the Riemann tensor is 0, ni of the m is identity plus order epsilon cube. In the product, yeah, this I have to establish, right? So I said, let's suppose that the m for the whole thing is a product of m for each segments. Then for each segment, this is the correct result, right? Okay, so I have not proven that this, so that there's a, gap in the proof so far, right? That assuming that m of the whole thing is given by product of m for each segment, then this is true. Okay, this I have not proven, right? I'm going to prove after this. I'm just outlining how the argument will go. Once we have gotten a form like this, then we can check that when we expand it out, each term, you see, this is 1 over n to the 3 half, and this will give you at most n terms, right? So this sum is of order n. So in the n goes to infinite limit, this gives you 0. In higher parts, you can check how many terms you will have, right? N into n minus 1 by 2, n into n plus 1 by 2 terms you will get from the product of 2 of the bi's. Right? That goes as n squared, right? But you have 1 over n cube. Each term goes to 0. Okay, so this product becomes, so this approaches identity as n goes to infinity. But n is up to us to choose, right? If I can prove that this m is identity in any one way, right, it better be identity, right? It doesn't, the MAAC is something that you calculate on this, right, by remaining on this curve. It doesn't matter how you calculate it. As long as you have found one way of calculating it and show that it's identity, right, any other way of calculating it will give you identity. Exactly. 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 Right. You see, if the original, if the order epsilon square term was present, right, which would be the case if the Riemann tensor was non-zero, then this argument would not work, because you will get order 1 over n. Right, epsilon square is 1 over n, and then you have n terms, each of order 1 over n. They can add up to give something of order 1. Right. So it's crucial that the order epsilon square term is basic, right, and that happens only when the Riemann tensor is 0. Exactly. The denominator has a higher exponent, right? Exactly. Yes. This one? Oh, this product. I have not proven it, right? I've just said intuitively you can think of the C as a product of these things, right? But you have to make sure that all the internal things cancel out, right? So I'll explain how that proof goes. Okay. Exactly. So we'll deal with that. I agree. We'll deal with that because they are matrices, right? We cannot just multiply them. Okay. So that we'll deal with. If they are just phases, right? Some numbers, then it's clear that this proof will work, right? Because numbers doesn't matter in which order you multiply. Yeah. So we have to do a little more manipulation, but we will see how exactly we go about doing this, right? So the goal is to express m as a product of n terms like this, right? And I think what people are objecting to is that it's not just the product of each segment, right? Because you have the internal lines all have to be cancelled out, right? And the order matters, right? So you'll see how exactly we do this. Is it clear? Okay. So as long as we can bring it into this form, we are done, right? So our now next goal is to try to see how M can be brought into this form. So let me draw this curve again. C. And you want to calculate MAAC. Okay. So the strategy will be to swallow the area segments one by one. Okay, and I'll explain what this means. Okay. The idea is that you have to make sure that you don't need more than n steps, that we can express this as a product of n terms, right? Not n to the 3/2 terms. Then the problem will come back again, right? You have to make sure that we have n factors of that kind. Okay. So the strategy is to swallow it one by one. What does it mean? Which means that starting with this, we will show that if we take another curve, so this was the original curve. I think I should draw, maybe I have to draw several pictures. Let me draw it. Now I want to draw this is C, so this is C prime. Okay. I have eaten up a little segment, right, of that size epsilon. Okay. And what we want to prove is that M AC is equal to M AA C prime times a matrix of order 1 plus order 1 over n to the 3/2. If we can do this, then you are done, because then we will start with C prime, right, which is here, and eat up some other segment from somewhere else, right? And this way we can just eat up all the n segments. Is that clear? Because
Area lost is order 1 over n.
yes, area loss, because each element has order 1 over n, right? Okay. We have to make sure that wherever you pick this area, right, because our initial point is fixed. Okay. We have to make sure that wherever you pick, decide to cut off this area, right, from this curve, we always have this structure. Because then your order doesn't matter. You just cut off one by one, right, little by little, all the area segments, and reduce the curve to a point, right, for which M is obvious identity. Is this clear? Okay. So if you can prove this, then you are done. Okay. So for this, let's try to do another. Let's call this point B. And then this little curve we'll call C double prime. Okay. This one?
Yeah.
This to be proven. Need to prove. So what I was trying to say is if we can prove this, then we are done, right? Because one by one we will remove those areas and we will pick up terms like this, right? And at the end we will be left with n terms like this. So what I'm going to do is that this curve, so ultimately we are interested in going along this curve, right? This is our C prime. Okay? It's clear? So what I have to do is to go from here to here. Let me write the equation and then I think it will become clearer. Okay, last time we had derived some relation. Okay, if you remember, so M A C, I can first write in terms of MBBC. So this is M A B C inverse M BBC times M ABC. Well, this is C1. Let me write M C1. Right? This is the curve C1. This part is what I'm calling C1. Okay, that's A to B. You remember this relation? Okay, you went, so the first we apply MABC, so you go like this. Okay. Then you go like this, and then you go like this. Right? That's what did I do? No, then you sorry, you go like this, okay. Then you go all the way back to B, and then you come back. So this one I write is clear. So MBBC is going starting from here and going like this. Okay. But we are going to do something a little strange. We will have the path, we go like this, then come back and then go down. That's the same path. Because we go like this, then like this, but immediately we follow it back, right? And then we come back like this. Pardon? Exactly. So this will be, so MBBC, I can write as MBBC prime, C double prime first. C double prime is this little curve, yellow curve. And then M B B, but this time this is along the curve C prime. Because you see, you go like this, right? That is M B B C double prime. And then you go from B back to B, right? But that curve is C prime, right? C prime is the white curve. Right? I mean, in this picture, C prime is the white curve and C double prime is the yellow curve. Is this clear? C was the original curve. Is this clear? No? And then you have the M and M inverse outside. is C1, sorry, A may be C1. This one? Oh, MBBC is we want to go from here to like this. Okay, so what we did, we went round first, then backtracked and went like this. And then go back because see this part gets cancelled because we come like this and immediately go back, right? Parallel transport is reversible, we are saying, right? So as long as you come like this and follow immediately backwards, right? It's the inverse matrix, right? So this part will not contribute. Yes, that is MBBC prime. Going back, let's see, you go like this and then like this, right? Is that clear? So this gives you MAB C1 inverse, MBB C prime, and then no, I'm going to insert MAB C1, MAB C1 inverse, and then M. Is this clear? C1, yes, both are all are MAB or always C1. I have just inserted MAB C1 or M inverse AB C1. That's all. Okay. No, why? This one? No, it doesn't imply that MAS is identity, right? Because these are different, right? Why should it be identity? See, MBBC. So I have just converted written MAAC, right, which was along the original curve like this, in terms of some curve which is C prime. Okay, that's yeah. So that's C prime and then BBC double prime. So the only pictorial thing that you have to see, this relation we had derived earlier, right? That changing origin, right? The changing origin, that if you want to go like this and if you want to go like this, the way we can go, we can relate the two is that you first go from here to here, then go all the way and then come back. Okay? That is this relation. Okay. After that, we keep this aside. We are just manipulating this MBBC. Okay. MBBC is starting from B and going to B. Okay, but along the outer curve. Okay. Then we said that okay, we travel the outer curve by first completing a small loop here, and then going back along the small loop and coming back all the way. That's the same as doing the outer curve. Okay. But in that process, we have written as a product of two terms. One is the loop, this loop contribution, the small loop contribution, that is MBBC double prime, and then the movement along the C prime, starting from B, will come back to B, but this time along C prime. Okay, you should just remember that what acts first should be on the right, right? So it's acting on the vector by left multiplication. Now this one is 1 plus order 1 over n to the 3 half. Because it's a small loop. This one is not small in any by any means, right? Because you want to move to arbitrary point, arbitrary row, right? This group is not close to A in any sense. So this is of order 1 matrix. But it doesn't matter because this is inverse of this. So identity will remain identity, right? And order 1 over n to the 3 half matrix, right? When you multiply by 2 finite matrices, it remains order 1 over n to the 3 half. So this whole combination, so this then can be written. Okay, the next step is M A B C1 inverse. Pardon?
The first 3 matrices can directly make M.
Yes, thank you. No, it's A, that exactly. Thank you. So first 3 matrices. This one, right, is basically changing origin from B to A on C prime, right? The loop is C prime. So this is M A C prime times 1 plus order 1 over n to the 3 half. Okay, the crucial point is that even though there are finite matrices over here, right, it conjugates the my matrix close to identity, right? And when it conjugates a matrix close to identity, it remains a matrix close to identity, right? The fact that there are these finite matrices doesn't matter. So now we are done, right? We have proven that MAAC is MAAC prime times 1 plus order 1 to the n over n to the 3 half. And now you can repeat this. You can start with C prime and cut out some other region somewhere else, right? We can do it here or we can do it somewhere else, doesn't matter, right? In whichever order you do it, you slowly shrink the curve and you can do it in n steps, right? Because you are just eating up n segments one by one. So you'll need n steps. In each step, we get some MAA C prime. This is a new curve and something of order 1 over 1 plus order 1 over n to the 3 half. At the end, the curve C prime has become a point, right? That has identity. That of course is identity, right? You're not moving at all. So whatever is left is a product of n matrices, each of order 1 plus 1 over n to the 3 half. Right? So that basically establishes what you wanted to prove. Right? So this shows the conclusion is that MAAC is identity, right? Proven by taking n. Okay, but of course it's identity provided you can find a surface on which the Riemann tensor vanishes. Okay, if the Riemann tensor doesn't vanish, then you get n terms, but each of order 1 plus 1 over n. Right? So that doesn't help, right? That product can become finite. Is this clear? So this gives a geometric picture of what Riemann tensor is, right? It basically captures the effect of curvature so that if you take a vector and parallelly transport it along a curve, it doesn't come back to the original vector. Is this clear?
If it is 0, it will come back to.
If the Riemann tensor is 0, yes, indeed. If the Riemann tensor is 0 on that surface, right? Elsewhere it doesn't matter. You have to find one surface on which Riemann tensor is 0 everywhere. then the vector will always come back to itself. That somewhere on that curve, the Riemann tensor must be non-zero. That the space is curved. Right? In flat space, parallel transport come back to the origin. Okay. Flat space which is simply connected, right? The point is, suppose the space is not connected, simply connected, right? This surface that we get, okay, you cannot that you may have a curve, right? But you may not be able to find a surface that whose boundary is this curve. Then that doesn't help, right? Imagine that I take a piece of paper, maybe. Pardon? What is the question? Loop on a torus. Well, torus is flat. I mean, you have to do a little more. Let me try to read this. That imagine that you draw something like this, slight slant, right? Pardon? Tapered cylinder. So on this, the curvature is 0 everywhere. Because originally the paper was flat. Here it's 0, right? All I have done is that I have just I mean this without stretching, right? The metric is the same. Because no notion of distance hasn't changed, right? I have not stretched the paper, right? So the metric remains the same, that the curvature Riemann tensor remains 0 on this surface. Okay? But on this surface, parallel transport, right, can change the vector, okay? Because it has a hole. Okay? So if we draw, let me try to draw this. These two vectors are parallel if you move along this, right? But if you, I didn't draw it in the right place, I have to somehow make this. Okay, let me draw a better thing maybe. Okay, yeah, it's a, well, imagine there is a small hole left outside, right? It's a tapered cylinder. Okay, these two curves don't look parallel, right? You can go from here to here. It's, well, they don't look parallel, but their angle is not 90 degrees, right? But if you go on the other side, then their angle is 90 degrees, right? So the notion of parallel transport changes. You see, okay, let me draw a curve like this. These and these are parallel, right? But suppose you now change the two lines which are originally parallel doesn't look parallel anymore. Okay? And that's because there's a hole sitting here. Even though the thing is flat, right? There's a hole sitting there. If you close it, right? If you make it into a cone, okay, then also it's the same problem. Right? But once you make it into a cone, then you can attribute that there is at the tip of the cone there's a Riemann tensor. Okay? You recognize that there is a Riemann tensor sitting at the singular point just by seeing that the parallel transport along this closed curve, okay, doesn't bring you back on the original form. Right? Because these two were parallel. If you go like this, then these two are parallel, these two vectors. Okay? But if you go like this, they are not parallel. Because it's path dependent, which means along a closed curve, there is a non-trivial parallel transport. Pardon? Non-identity, exactly. Right? So whenever you have curve, whenever you have parallel transport that produces a change, right? When non-identity matrix, right? Then you know either the that there is no closed surface that you can draw on which Riemann tensor is zero everywhere, or that the space as whole, right? The Riemann tensor may vanish everywhere on the space, but if it has a hole, right, then the closed surface may not close. Where M can be zero. Well, say zero, no, it cannot be zero because you saw that it preserves norm. Remember the DDU of Gij, Ni, Nj is zero, right? DDU of Gij, Ni, Nj is zero, right? So if we come back to the original point, x naught, closed curve, then at x naught, Gij is the same, right? So if original vector was not zero, right, the final vector cannot be zero, right? Because it's a non-zero result. I mean, if the original vector was not zero, then Gij, Ni, Nj was not zero, right? It cannot become zero at the end. Well, no, it cannot be made very, very small also along a closed curve because this norm is fixed, right? So for a given metric, right, you cannot do very much to change this because of the conservation of the norm. Okay, so I think maybe I'll stop here today. So we'll have to say a few more words about Riemannian geometry and then we'll start with gravity, right? Why Riemannian geometry is related to gravity. Yes.